up until this time when we've integrated, we've always had a finite interval that we've integrated over, or we've had a function that's been defined in finite values over the interval. What we're going to do in this section is we're looking at what's called improper integrals. That's where either the interval that you're integrating over is infinite, or it's where the function's values over that interval somewhere are infinite. So we're going to figure out how to calculate those values in some cases. Okay, so our strategy here is, let's say that we're trying to find the integral from 1 to infinity of the function 1 over x squared. If you graph that function, y equal 1 over x squared, you get this curve. And if we're integrating that from 1 to some interval b, we can find that area under that curve. It's going to be a finite area. Okay, so now what we're going to do, if we're trying to integrate it, though, from 1 to infinity, where the x value is going all the way out, you know, and you can see that the function's always a little above the x-axis, so we're always adding more area the further x, you know, goes down the x-axis. What we're going to do is we're going to move the b so that it is further down. And each time we look at a specific b, we will have a finite area here that we can calculate. Okay? So the way we calculate this integral is we're going to look at the integral from 1 to some value b, which is defined, and then we're going to assume that the b is getting larger and larger. So we're taking the limit as the b, that upper limit on the integration, is getting closer and closer to infinity. So at each point, we can calculate this area. Then we're going to be able to calculate it from here to here. Then we're going to calculate the area from here to here. And just keep letting that b get larger and larger. And then we're going to see, do those values we get for those areas, or those integrals from 1 to b, approach some number? So you're looking at the limit of those integrals that are going to be finite, and just seeing if they're getting closer to some fixed value. Sometimes they don't. Sometimes that little bit of area that you are continually adding as x gets larger is so substantial that it never converges to anything. It's never getting closer and closer to some number. It might continue to grow. And in that case, we'd say that that improper integral is undefined. It would be infinite. So let's look at a couple problems here. Okay. So now what the situations that we might have here is where the interval is infinite. So let's say that we're trying to find the integral from a to infinity. So we've got this integral from a to infinity of a function f. The function is defined on that entire interval. That's going to be the same thing as the limit. We're replacing the infinity with some fixed number b, so that we're just going to be calculating that area from a to b then. And then we're going to take the limit as we let the b go to infinity. So you're just replacing that upper limit with some fixed value, and then letting that value get closer to infinity. So that's one way to rewrite it. Let's say we were looking at the integral from minus infinity here to b. Well, in this case, it's the lower limit that's the infinite end. So we're going to replace it with some fixed number a. So instead of really going from b all the way out to the left, we're going to stop at some a here, and then we're just going to calculate that interval, that integral, and then assume that the a is getting smaller and smaller. So we'll look at the limit as a goes to minus infinity. Now let's say it's infinite on both ends, so the function's actually continuous on the interval from minus infinity to infinity. But if we were actually calculating that integral, we would be looking at that area that's infinite in both directions. So what we're going to do is we're going to chop it at some point in the middle. Then we're going to look at the integral from c to b, because I can change from minus infinity to infinity, if that's what I'm trying to get the integral for. I can rewrite that by fixing some number in the middle and splitting that into from minus infinity to c, plus the integral from the c to infinity. So I'm just looking at it in two pieces. And now this one, to calculate that improper integral, I would replace that with the limit. I would put an a is the lower limit for that integral and keep the c fixed. And now I'm letting the a go toward minus infinity. And then the second one, I'm going to replace the upper limit, the infinity, here with some value b. So I'll be going from c to b. And then I'm going to take that limit as the b goes to infinity. So we're just doing it as in two pieces here, this one, and we're going to be taking the limit in both directions. We only want one of the two limits to be infinity at any given time. So that's why you'll rewrite that to be this plus this one if you have both limits are infinite or minus infinity. Okay, if the limit exists, we say that the improper integral converges. If it does not exist, then the improper integral diverges. So we'll see if that limit exists or not to determine if that infinite integral can exist. Okay, so now this infinite interval. This is where we have an interval that is actually infinite. So we're integrating from 0 to infinity, and the function's e to the minus 3x. So e to the minus 3x would have the value of 1 at 0, and it's going to continue to go out to the right. It's infinite that way, and we're trying to go from 0 and measure all the area. The areas continue out here. Okay, so now, first step is to rewrite the improper integral as a limit. We're going to replace that infinity with some number. I can use a or b, whatever number you want. Let's use b. And then we're going to take the limit as the b goes to infinity. Now, the next step is just to calculate this integral. That integral, e to the minus 3x, you would need a u substitution. U is minus 3x. So this is going to come out to be minus 1/3 e to the minus 3x, and then we evaluate that from 0 to b. So do your u substitution, and you should get this for the antiderivative. And remember, I've still got this limit out here in front, and I'll worry about that at the very end. Okay, so now, evaluating at b and at 0, this is going to be the limit again, as b goes to infinity. Minus 1/3 e to the minus 3b, and then minus negative 1/3 e to the 0. So I'm just plugging in the b, and then plugging in the 0 and subtracting them. Okay, the next step, when I have an e to a negative power, it's harder for me to see what the limit's going to be. So what I'm going to do is I'm going to change it so it's a positive power. E to the 0 I know is just 1. So this is just 1. Okay, and I'm going to change that first expression. That's negative 1/3 e to the 3b. I want a positive exponent so I can more easily see what the value of that function is going to approach. And then I've got plus just a 1/3 added on. Okay, so now here's where we're taking the limit. We've evaluated 0b, take the limit. I'm going to let b get larger and larger. As the b gets larger and larger, e to that 3b is getting larger and larger. And so now that's in the denominator of a fraction. If that denominator is getting larger and larger, but the numerator is staying fixed, negative 1, or negative 1/3, then this expression here is going to be approaching 0. And so now this is just a constant value, so this limit would be 0 plus the 1/3. The limit's actually 1/3. That means that this integral does converge. So e to the minus 3x dx from 0 to infinity converges, and it converges to the number 1/3. So what that means area-wise, we're trying to find that infinite area. The area goes on and on. But what this is saying is that this function is tapering off so greatly out here on the right side that it's getting closer and closer to 1/3. The further you let that be on the x-axis, then the closer that area is getting to 1/3. It doesn't ever reach at 1/3. It's because you're constantly adding a little bit more, but it's going to be getting closer and closer to 1/3 as you go further out. And that's what we mean by convergence. Okay? Similar type problem. We have our limits from 0 to infinity. Our function's 1/1 plus x squared. Now you can see here in the graph that if we're trying to find the area under this function from 0 to infinity, we're going to have an infinite area because that function is above the x-axis always, and there's always some area that we're going to continue to be adding as that b gets further and further, down the x-axis. Okay, first thing I'm going to do to try to evaluate this is I'm going to rewrite it as a limit. The part that has the infinity, I'm going to replace that with a or b, just some number. So I'll put a b, and we're going 0 to b, and then we're just going to take that integral of 1 over 1 plus x squared, and we're going to then take the limit of whatever that comes out to be as b goes to infinity. Okay. I need to worry about this here. I need to integrate 1 over 1 plus x squared, which hopefully you recognize that being an inverse tangent derivative. So this comes out to be, this is the limit, inverse tangent of x. Okay? And I'm going to evaluate that from 0 to b. Okay, so I've got my limit, b approaches infinity. Replace the variable x with b and then with 0. So I'm going to have inverse tangent of b minus inverse tangent of 0. Okay, now we need to find what those inverse tangent values are. Okay, I'm going to break this up into two parts. I'm going to look at this since the variable b is in just the first part. This is the limit of inverse tangent of b as b approaches infinity minus the limit of inverse tangent of 0 as b goes to infinity. Of course, you don't see a b in that second expression. Inverse tangent of 0, all we need to do is figure out what this value actually is. This is the one that we're going to have to worry about, the limit, is that b is changing. So now let's look at our tangent function. You should know what the graph of the tangent function looks like. Tangent has its vertical asymptotes at minus pi over 2 and pi over 2. Inverse tangent is only defined, if you look back at when it was defined, it's only defined to have a value between minus pi over 2 and pi over 2. Okay? So the angle must be between those two values. Okay, so now, if you graph this, we've got a vertical asymptote at minus pi over 2 and at pi over 2. Also, the tangent function passes through 0 when the x is 0. Now, this is the graph of y equal to tangent. I'm not graphing the inverse function. I'm graphing y equal to tangent of x. And then this is the way the function approaches those asymptotes. Okay, so now, inverse tangent's looking at y values. So if I want to know inverse tangent of 0, look at where is the value 0. Remember, inverse tangent takes an angle and gives you a value. Inverse tangent is actually taking a value and returning the angle. Remember, inverse tangents just reverse the x and the y values. They replace the values and angles. So inverse tangent of 0 says, this is my value. That's the y value. Now, what's the angle that corresponds to it? Well, look in the graph. The value of 0 for y corresponds to the angle being 0. So inverse tangent is 0. So this one is just going to be 0. And now let's look at the other function. Inverse tangent of b is getting closer to infinity. So this says the values are getting closer to infinity, positive infinity. So the values are approaching infinity. Where in this graph are the values approaching infinity? Well, the y values will be getting closer and closer to infinity right here. So what is that angle as the y values are approaching infinity? This is the angle. The inverse function is the angle, and that will be just pi over 2. So we have pi over 2 for this first limit, 0 for the second, since inverse tangent of 0 is 0. And so our answer here is actually pi over 2. So what that means is that this infinite area that we were trying to calculate under the function 1 over 1 plus x squared from 0 to infinity, that's an infinite region that we're trying to calculate an area for, it actually is convergent. It's getting closer and closer to the value pi over 2. So 3.14 over 2 is what that area is accumulating to. So even though you're going continually further and further out and adding a little bit more area, that area is tapering off so quickly as you go further out the x-axis that it's never actually even reaching pi over 2. It's going to be a little less than that, and it's getting closer and closer to pi over 2 the further out you go. So that's what we mean by this integral converges, and it's convergent to the value pi over 2.